Hey, so I had this idea. This is a Möbius strip. And I was thinking before about leptons and quarks and, how particles can be point-like and yet still have a wave function. And in physics, whenever something seems impossible, you just add an extra dimension to the point. And so I've turned this point into a line, theoretically, even though this is a 3D object, but we can imagine that this strip is a flat bit of space-time. And literally what the quarks and leptons are doing is they're traveling these closed curvature loops, which is the Möbius strip. Now, the interesting thing about this is, if I can find a pair of scissors, one sec. So, imagine this is your quark, so your fundamental particle. Now, beginning of the universe, if the expansion rate exceeds the ability for the quark to remain point-like, what ends up happening is something like this. So if I cut along this point, if I try to cut this point in half, the field itself does not separate, but the excitations in that field become even more looped. Now, this can go even further. If you take the duality of that fundamental field, quark, anti-quark, and you cut that in half, just watch what happens. A good grip on it. This is actually something I discovered as a kid when I did this. The Möbius strip. You get two Möbius strips. Double twisted Möbius strips. So this is like the entanglement of all reality, and like you can keep doing this. Like theoretically, if the paper was wide enough, you could keep cutting that Möbius strip in half, and eventually you would get every entangled field state in the universe. Just for example, I've cut one of these halves again, and if we follow the curvature that this theoretical particle takes, just follow it round, goes under there, goes through there. Don't know if you can see that, but that's the one piece. You can keep going. And eventually you get to the bit in the paper where I've joined with cellophane tape. There it is. So the other thing is, like, what's the difference between like a quark and say like an electron? Well, it's to do with the number of twists that that particle has to take. So if we imagine that this is the this thicker bit, right? This is the quark anti-quark pair, and this is its electron. And because this is a much bigger fundamental particle, than the electron field itself, the electron field kind of keeps it bound and locked in that central point there. Can you see that central point? So you've got an entire field of the universe, kind of looks like a butterfly, and these field states are entangled with themselves through these geometric twists, and that's what keeps matter together. Now, it's important to note that this is not a substitute for real physics, but it is a good way of thinking about space-time curvature. And especially if everything, as physics says, was originally a single point of infinite density that expanded out of the vacuum, what we can imagine is that if that expansion rate reached a point where these loops were stretched to a kind of infinity, you can end up inadvertently creating the energy needed to create everything in the universe. Because as you try to separate the Möbius strip from itself, it will just duplicate and populate another quark or anti-quark, whichever side of the field needs to be balanced. But yeah, good analogy.